Welcome to the audiobook of Conjectures and Refutations by Karl, narrated by Elyse Hargreaves with the consent of the University of Klagenfurt, Karl Library. Chapter 10, Truth, Rationality, and the Growth of Scientific Knowledge. 1. The Growth of Knowledge, Theories and Problems. My aim in this lecture is to stress the significance of one particular aspect of science, its need to grow, or, if you like, its need to progress. I do not have in mind here the practical or social significance of this need. What I wish to discuss is rather its intellectual significance. I assert that continued growth is essential to the rational and empirical character of scientific knowledge, that if science ceases to grow, it must lose that character. It is the way of its growth which makes science rational and empirical, the way, that is, in which scientists discriminate between available theories and choose the better one, or, in the absence of a satisfactory theory, the way they give reasons for rejecting all the available theories, thereby suggesting some of the conditions with which a satisfactory theory should comply. You will have noticed from this formulation that it is not the accumulation of observations which I have in mind when I speak of the growth of scientific knowledge, but the repeated overthrow of scientific theories and their replacement by better and more satisfactory ones. This, incidentally, is a procedure which might be found worthy of attention, even by those who see the most important aspect of the growth of scientific knowledge in new experiments and in new observations. For our critical examination of our theories leads us to attempts to test and to overthrow them, and these lead us further to experiments and observations of a kind which nobody would ever have dreamt of without the stimulus and guidance both of our theories and of our criticism of them. For indeed, the most interesting experiments and observations were carefully designed by us in order to test our theories, especially our new theories. In this paper, then, I wish to stress the significance of this aspect of science and to solve some of the problems, old as well as new, which are connected with the notions of scientific progress and of discrimination among competing theories. The new problems I wish to discuss are mainly those connected with the notions of objective truth and of getting nearer to the truth, notions that seem to me of great help in analysing the growth of knowledge. Although I shall confine my discussion to the growth of knowledge in science, my remarks are applicable without much change, I believe, to the growth of pre-scientific knowledge also, that is to say, to the general way in which men, and even animals, acquire new factual knowledge about the world, the method of learning by trial and error, of learning from our mistakes, seems to be fundamentally the same whether it is practiced by lower or by higher animals, by chimpanzees or by men of science. My interest is not merely in the theory of scientific knowledge, but rather in the theory of knowledge in general. Yet the study of the growth of scientific knowledge is, I believe, the most fruitful way of studying the growth of knowledge in general. For the growth of scientific knowledge may be said to be the growth of ordinary human knowledge writ large, as I have pointed out in the 1958 preface to my Logic of Scientific Discovery. But is there any danger that our need to progress will go unsatisfied, and that the growth of scientific knowledge will come to an end? In particular, is there any danger that the advance of science will come to an end because science has completed its task? I hardly think so, thanks to the infinity of our ignorance. Among the real dangers to the progress of science is not the likelihood of its being completed, but such things as lack of imagination, sometimes a consequence of lack of real interest, or a misplaced faith in formalization and precision, which will be discussed below in section 5, or authoritarianism in one or another of its many forms. Since I've used the word progress several times, I had better make quite sure at this point that I am not mistaken for a believer in a historical law of progress. Indeed, I have before now struck various blows against the belief in a law of progress, and I hold that even science is not subject to the operation of anything resembling such a law. The history of science, like the history of all human ideas, is a history of irresponsible dreams, of obstinacy, and of error. But science is one of the very few human activities, perhaps the only one, in which errors are systematically criticized and fairly often, in time, corrected. This is why we can say that in science, we often learn from our mistakes, and why we can speak clearly and sensibly about making progress there. In most other fields of human endeavour, there is change, but rarely progress, unless we adopt a very narrow view of our possible aims in life. For almost every gain is balanced, or more than balanced, by some loss, and in most fields, we do not even know how to evaluate change. Within the field of science, we have, however, a criterion of progress. Even before a theory has ever undergone an empirical test, we may be able to say whether, provided it passes certain specific tests, it would be an improvement on other theories with which we are acquainted. This is my first thesis. To put it a little differently, I assert that we know what a good scientific theory should be like, and even before it has been tested, what kind of theory would be better still, provided it passes certain crucial tests. It is this meta-scientific knowledge which makes it possible to speak of progress in science and of rational choice between theories. Thus, it is my first thesis that we can know of a theory, even before it has been tested, that if it passes certain tests, it will be better than some other theory. My first thesis implies that we have a criterion of relative potential satisfactoriness, or of potential progressiveness, which can be applied to a theory even before we know whether or not it will turn out, by the passing of some crucial tests, to be satisfactory in fact. This criterion of relative potential satisfactoriness, which I formulated some time ago, and which, incidentally, allows us to grade theories according to their degree of relative potential satisfactoriness, is extremely simple and intuitive. It characterizes as preferable the theory which tells us more. That is to say, the theory which contains the greater amount of empirical information or content, which is logically stronger, which has the greater explanatory and predictive power, and which can therefore be more severely tested by comparing predicted facts with observations. In short, we prefer an interesting, daring, and highly informative theory to a trivial one. All these properties which, it thus appears, we desire in a theory can be shown to amount to one and the same thing, to a higher degree of empirical content or of testability. My study of the content of a theory, or of any statement whatsoever, was based on the simple and obvious idea that the informative content of the conjunction A-B of any two statements, A and B, will always be greater than, or at least equal to, that of any of its components. Let A be the statement, "It will rain on Friday," B the statement, "It will be fine on Saturday," and AB the statement, "It will rain on Friday and it will be fine on Saturday." It is then obvious that the informative content of this last statement, the conjunction AB, will exceed that of its component A and also that of its component B. And it will also be obvious that the probability of AB, or what is the same, the probability that AB will be true, will be smaller than that of either of its components. For the next paragraph, I am going to be displaying two formulas on the screen, so please view the screen to follow along. Writing CT in brackets A for the content of the statement A and CT in brackets AB for the content of the conjunction A and B, we have formula number 1. CT in brackets A is less than or equal to CT in brackets AB, which is greater than or equal to CT in brackets B. This contrasts with the corresponding law of the calculus of probability. Formula number 2. P in brackets A is greater than or equal to P in brackets AB, which is less than or equal to P in brackets B, where the inequality signs of formula number 1 are inverted. Together, these two laws, 1 and 2, state that with increasing content, probability decreases, and vice versa, or in other words, that content increases with increasing improbability. This analysis is, of course, in full agreement with the general idea of the logical content of a statement as the class of all those statements which are logically entailed by it. We may also say that a statement A is logically stronger than a statement B if its content is greater than that of B, that is to say, if it entails more than B does. This trivial fact has the following inescapable consequences. If growth of knowledge means that we operate with theories of increasing content, it must also mean that we operate with theories of decreasing probability, in the sense of the calculus of probability. Thus, if our aim is the advancement or growth of knowledge, then a high probability, in the sense of the calculus of probability, cannot possibly be our aim as well. These two aims are incompatible. I found this trivial, though fundamental result about 30 years ago, and I have been preaching it ever since. Yet the prejudice that a high probability must be something highly desirable is so deeply ingrained that my trivial result is still held by many to be paradoxal. Despite this simple result, the idea that a high degree of probability, in the sense of the calculus of probability, must be something highly desirable, seems to be so obvious to most people that they are not prepared to consider it critically. Dr. Bruce Brooke-Wavel has therefore suggested to me that I should stop talking in this context of probability and should base my arguments on a calculus of content and of relative content. Or, in other words, that I should not speak about science aiming at improbability, but merely say that it aims at maximum content. I have given much thought to this suggestion, but I do not think that it would help. A head-on collision with the widely accepted and deeply ingrained probabilistic prejudice seems unavoidable if the matter is really to be cleared up. Even if, as would be easy enough, I were to base my own theory upon the calculus of content or of logical strength, it would still be necessary to explain that the probability calculus, in its logical application to propositions or statements, is nothing but a calculus of the logical weakness or lack of content of these statements, either of absolute logical weakness or of relative logical weakness. Perhaps a head-on collision would be avoidable if people were not so generally inclined to assume, uncritically, that a high probability must be an aim of science, and that, therefore, the theory of induction must explain to us how we can attain a high degree of probability for our theories. And it then becomes necessary to point out that there is something else, a truth-likeness or verisimilitude, with a calculus totally different from the calculus of probability with which it seems to have been confused. To avoid these simple results, all kinds of more or less sophisticated theories have been designed. I believe I have shown that none of them is successful. But what is more important, they are quite unnecessary. One merely has to recognize that the property which we cherish in theories, and which we may perhaps call verisimilitude or truth-likeness, see section 6 below, is not a probability in the sense of the calculus of probability, of which formula number 2 is an inescapable theorem. It should be noted that the problem before us is not a problem of words. I do not mind what you call probability, and I do not mind if you call those degrees for which the so-called calculus of probability holds by any other name. I personally think that it is most convenient to reserve the term probability for whatever may satisfy the well-known rules of this calculus, which Laplace, Keynes, Jeffreys, and many others have formulated, and for which I have given various formal axiom systems. If and only if we accept this terminology, then there can be no doubt that the absolute probability of a statement A is simply the degree of its logical weakness or lack of informative content, and that the relative probability of a statement A, given a statement B, is simply the degree of the relative weakness or the relative lack of new informative content in statement A, assuming that we are already in possession of the information B. Thus, if we aim, in science, at a high informative content, if the growth of knowledge means that we know more, that we know A and B rather than A alone, and that the content of our theories thus increases, then we have to admit that we also aim at a low probability in the sense of the calculus of probability. And since a low probability means a high probability of being falsified, it follows that a high degree of falsifiability or refutability or testability is one of the aims of science. In fact, precisely the same aim as a high informative content. The criterion of potential satisfactoriness is thus testability or improbability. Only a highly testable or improbable theory is worth testing and is actually, and not merely potentially, satisfactory if it withstands severe tests, especially those tests to which we could point as crucial for the theory before they were ever undertaken. It is possible, in many cases, to compare the severity of tests objectively. It is even possible, if we find it worthwhile, to define a measure of the severity of tests. See the addenda to this volume. By the same method, we can define the explanatory power and the degree of corroboration of a theory. The thesis that the criterion here proposed actually dominates the progress of science can easily be illustrated with the help of historical examples. The theories of Kepler and Galileo were unified and superseded by Newton's logically stronger and better testable theory, and similarly, Fresnel's and Faraday's by Maxwell's. Newton's theory and Maxwell's, in their turn, were unified and superseded by Einstein's. In each such case, the progress was towards a more informative and therefore logically less probable theory, towards a theory which was more severely testable because it made predictions which, in a purely logical sense, were more easily refutable. A theory which is not in fact refuted by testing those new and bold and improbable predictions to which it gives rise can be said to be corroborated by these severe tests. I may remind you in this connection of Galard's discovery of Neptune, of Hertz's discovery of electromagnetic waves, of Eddington's eclipse observations, of Elsasser's interpretation of Davison's maxima as interference fringes of Du Bois waves, and of Powell's observations of the first Yukawa mesons. All these discoveries represent corroborations by severe tests, by predictions which were highly improbable in the light of our previous knowledge, previous to the theory which was tested and corroborated. Other important discoveries have also been made while testing a theory, though they did not lead to its corroboration, but to its refutation. A recent and important case is the so-called refutation of parity, and Lavoisier's classical experiments, which show that the volume of air decreases while a candle burns in a closed space, or that the weight of burning iron filings increases, do not establish the oxygen theory of combustion, yet they tend to refute the phlogiston theory. Lavoisier's experiments were carefully thought out, but even most so-called chance discoveries are fundamentally of the same logical structure. For these so-called chance discoveries are, as a rule, refutations of theories which were consciously or unconsciously held. They are made when some of our expectations, based upon these theories, are unexpectedly disappointed. Thus, the catalytic property of mercury was discovered when it was accidentally found that in its presence a chemical reaction had been speeded up, which had not been expected to be influenced by mercury. But neither Oersted's, nor Roentgen's, nor Becquerel's, nor Fleming's discoveries was really accidental, even though they had accidental components. Every one of these men was searching for an effect of the kind he found. We can even say that some discoveries, such as Columbus's discovery of America, corroborate one theory of the spherical Earth, while refuting at the same time another, the theory of the size of the Earth, and with it, of the nearest way to India, and that they were chance discoveries to the extent to which they contradicted all expectations, and were not consciously undertaken as tests of those theories which they refuted. The stress I am laying upon change in scientific knowledge, upon its growth, or its progressiveness, may to some extent be contrasted with the current ideal of science as an axiomatized deductive system. This ideal has been dominant in European epistemology from Euclid's Platonizing cosmology, for this is, I believe, what Euclid's elements were really intended to be, to that of Newton, and further to the systems of Boscovic, Maxwell, Einstein, Bohr, Schrödinger, and Dirac. It is an epistemology that sees the final task and end of scientific activity in the construction of an axiomatized deductive system. As opposed to this, I now believe that these most admirable deductive systems should be regarded as stepping stones rather than as ends, as important stages on our way to richer and better testable scientific knowledge. Regarded thus as means or stepping stones, they are certainly quite indispensable, for we are bound to develop our theories in the form of deductive systems. This is made unavoidable by the logical strength, by the great informative content, which we have to demand of our theories if they are to be better and better testable. The wealth of their consequences has to be unfolded deductively, for as a rule, a theory cannot be tested except by testing, one by one, some of its more remote consequences, that is, which cannot immediately be seen upon inspecting it intuitively. Yet it is not the marvelous deductive unfolding of the system which makes a theory rational or empirical, but the fact that we can examine it critically, that is to say, subject it to attempted refutations, including observational tests, and the fact that, in certain cases, a theory may be able to withstand those criticisms and those tests, among them tests under which its predecessors broke down, and sometimes even further and more severe tests. It is in the repeated and flexible choice of a new theory that the rationality of science lies, rather than in the deductive development of the theory. Consequently, there is little merit in formalizing and elaborating a deductive system, intended for use as an empirical science, beyond the requirements of the task of criticizing and testing it, and of comparing it critically with competitors. This critical comparison, though it has, admittedly, some minor conventional and arbitrary aspects, is largely non-conventional, thanks to our Criterion of Progress. It is this critical procedure which contains both the rational and the empirical elements of science. It contains those choices, those rejections, and those decisions which show that we have learned from our mistakes and thereby added to our scientific knowledge. Yet perhaps even this picture of science, as a procedure whose rationality consists in the fact that we learn from our mistakes, is not quite good enough. It may still suggest that science progresses from theory to theory and that it consists of a sequence of better and better deductive systems. Yet what I really wish to suggest is that science should be visualized as progressing from problems to problems of ever-increasing depth. For a scientific theory, an explanatory theory is, if anything, an attempt to solve a scientific problem, that is to say, a problem concerned or connected with the discovery of an explanation. Admittedly, our expectations, and thus our theories, may precede, historically, even our problems. Yet science starts only with problems. Problems crop up especially when we are disappointed in our expectations, or when our theories involve us in difficulties, in contradictions, and these may arise either within a theory or between two different theories, or as the result of a clash between our theories and our observations. Moreover, it is only through a problem that we become conscious of holding a theory. It is the problem which challenges us to learn, to advance our knowledge, to experiment, and to observe. Thus, science starts from problems, and not from observations, though observations may give rise to a problem, especially if they are unexpected. That is to say, if they clash with our expectations or theories. The conscious task before the scientist is always the solution of a problem through the construction of a theory which solves the problem. For example, by explaining unexpected and unexplained observations. Yet every worthwhile new theory raises new problems, problems of reconciliation, problems of how to conduct new and previously unthought of observational tests. And it is mainly through the new problems which it raises that it is fruitful. Thus, we may say that the most lasting contribution to the growth of scientific knowledge that a theory can make are the new problems which it raises, so that we are led back to the view of science and of the growth of knowledge as always starting from and always ending with problems. Problems of an ever-increasing depth and an ever-increasing fertility in suggesting new problems. 2. The theory of objective truth, correspondence to the facts. So far, I have spoken about science, its progress, and its criterion of progress, without even mentioning truth. Perhaps surprisingly, this can be done without falling into pragmatism or instrumentalism. It is perfectly possible to argue in favor of the intuitive satisfactoriness of the criterion of progress in science without ever speaking about the truth of its theories. In fact, before I became acquainted with Tarski's theory of truth, it appeared to me safer to discuss the criterion of progress without getting too deeply involved in the highly controversial problem connected with the use of the word true. My attitude at the time was this: although I accepted, as almost everybody does, the objective or absolute or correspondence theory of truth, truth as correspondence with the facts, I preferred to avoid the topic, for it appeared to me hopeless to try to understand clearly this strangely elusive idea of a correspondence between a statement or a proposition and a fact. In order to recall why the situation appeared so hopeless, we only have to remember, as one example among many, Wittgenstein's Tractatus, with its surprisingly naive picture theory, or projection theory, of truth. In his book, a proposition was conceived as a picture or a projection or a photograph of the fact which it was intended to describe, and as having the same structure or form as that fact, just as a gramophone record is indeed a picture or a projection of a sequence of sounds, and shares some of its structural properties. Another of these unavailing attempts to explain this correspondence was due to Schlick, who gave a beautifully clear and truly devastating criticism of various correspondence theories, including the picture or projection theory, but who, unfortunately, produced in his turn another one which was no better. He interpreted the correspondence in question as a one-to-one correspondence between our designations and the designated objects, although counter-examples abound. Designations applying to many objects, objects designated by many designations, which refute this interpretation. All this was changed by Tarski's theory of truth and of the correspondence of a statement with the facts. Tarski's greatest achievement and the real significance of his theory for the philosophy of the empirical sciences is that he rehabilitated the correspondence theory of absolute or objective truth, which had become suspect. He vindicated the free use of the intuitive idea of truth as correspondence to the facts. The view that his theory is applicable only to formalized languages is, I think, mistaken. It is applicable to any consistent and even to a natural language, if only we learn from Tarski's analysis how to dodge its inconsistencies, which means, admittedly, the introduction of some artificiality or caution into its use. Although I may assume in this assembly some familiarity with Tarski's theory of truth, I may perhaps explain the way in which it can be regarded, from an intuitive point of view, as a simple elucidation of the idea of correspondence to the facts. I shall have to stress this almost trivial point because, in spite of its triviality, it will be crucial for my argument. The highly intuitive character of Tarski's ideas seems to become more evident, as I have found in teaching, if we first decide explicitly to take truth as a synonym for correspondence to the facts, and then, forgetting all about truth, proceed to explain the idea of correspondence to the facts. Thus, we shall first consider the following two formulations, each of which states very simply, in a meta-language, under what conditions a certain assertion of an object language corresponds to the facts. 1. The statement or the assertion, snow is white, corresponds to the facts if, and only if, snow is indeed white. 2. The statement or the assertion, grass is red, corresponds to the facts if, and only if, grass is indeed red. These formulations, in which the word indeed is only inserted for ease and may be omitted, sound, of course, quite trivial, but it was left to Tarski to discover that, in spite of their apparent triviality, they contained the solution of the problem of explaining correspondence to the facts. The decisive point is Tarski's discovery that, in order to speak of correspondence to the facts, as do 1 and 2, we must use a meta-language in which we can speak about two things, statements and the facts to which these statements refer. Tarski calls such a metalanguage semantical. A metalanguage in which we can speak about an object language but not about the facts to which it refers is called syntactical. Once the need for a semantical metalanguage is realized, everything becomes clear. Note that while 3, John called, is true, is essentially a statement belonging to such a metalanguage. 4, it is true that John called, may belong to the same language as John called. Thus, the phrase, it is true that, which, like double negation, is logically redundant, differs widely from the metalinguistic predicate, is true. The latter is needed for general remarks such as, if the conclusion is not true, the premises cannot all be true, or, John once made a true statement. I have said that Schlick's theory was mistaken. Yet I think that certain comments he made about his own theory throw some light on Tarski's. For Schlick says that the problem of truth shared the fate of some others whose solutions were not easily seen because they were mistakenly supposed to lie on a very deep level, while actually they were fairly plain and, at first sight, unimpressive. Tarski's solution may well appear unimpressive at first sight, yet its fertility and its power are impressive indeed. Thanks to Tarski's work, the idea of objective or absolute truth, that is, truth as correspondence to the facts, appears to be accepted today with confidence by all who understand it. The difficulties in understanding it seem to have two sources. First, the combination of an extremely simple intuitive idea with a certain amount of complexity in the execution of the technical program to which it gives rise. Secondly, the widespread but mistaken dogma that a satisfactory theory of truth should yield a criterion of true belief, of well-founded or rational belief. Indeed, this dogma underlies the three rivals of the correspondence theory of truth: the coherence theory, which mistakes consistency for truth; the evidence theory, which mistakes known to be true for true; and the pragmatic or instrumentalist theory, which mistakes usefulness for truth. These are all subjective or epistemic theories of truth, in contradistinction to Tarski's objective or metalogical theory. They are subjective in the sense that they all stem from the fundamental subjectivist position which can conceive of knowledge only as a special kind of a mental state, or as a disposition, or as a special kind of belief, characterized, for example, by its history or by its relation to other beliefs. If we start from our subjective experience of believing, and thus look upon knowledge as a special kind of belief, then we may indeed have to look upon truth, that is, true knowledge, as some even more special kind of belief, as one that is well-founded or justified. This would mean that there should be some more or less effective criterion, if only a partial one, of well-foundedness, some symptom by which to differentiate the experience of a well-founded belief from other experiences of belief. It can be shown that all subjective theories of truth aim at such a criterion. They try to define truth in terms of the sources or origins of our beliefs, or in terms of our operations of verification, or of some set of rules of acceptance, or simply in terms of the quality of our subjective convictions. They all say, more or less, that truth is what we are justified in believing or in accepting, in accordance with certain rules or criteria, of origins or sources of our knowledge, or of reliability, or stability, or success, or strength of conviction, or inability to think otherwise. The theory of objective truth leads to a very different attitude. This may be seen from the fact that it allows us to make assertions such as the following. A theory may be true, even though nobody believes it, and even though we have no reason to think that it is true. And another theory may be false, even though we have comparatively good reasons for accepting it. Clearly, these assertions would appear to be self-contradictory from the point of view of any subjective or epistemic theory of truth. But within the objective theory, they are not only consistent, but quite obviously true. A similar assertion, which the objective correspondence theory would make quite natural, is this. Even if we hit upon a true theory, we shall, as a rule, be merely guessing, and it may well be impossible for us to know that it is true. An assertion like this was made, apparently for the first time, by Xenophanes, who lived 2,500 years ago, which shows that the objective theory of truth is very old indeed, antedating Aristotle, who also held it. But only with Tarski's work has the suspicion been removed that the objective theory of truth as correspondence to the facts may be either self-contradictory because of the paradox of the liar, or empty and redundant, as Ramsay suggested, or barren, or at the very least redundant, in the sense that we can do without it. In my theory of scientific progress, I might perhaps do without it, up to a point. Since Tarski, however, I no longer see any reason why I should try to avoid it. And if we wish to elucidate the difference between pure and applied science, between the search for knowledge and the search for power or for powerful instruments, then we cannot do without it. For the difference is that in the search for knowledge, we are out to find true theories, or at least theories which are nearer than others to the truth, which correspond better to the facts, whereas in the search for powerful instruments, we are, in many cases, quite well served by theories which are known to be false. So one great advantage of the theory of objective or absolute truth is that it allows us to say, with Xenophanes, that we search for truth, but may not know when we have found it, that we have no criterion of truth, but are nevertheless guided by the idea of truth as a regulative principle, as Kant or Peirce might have said, and that though there are no general criteria by which we can recognize truth, except perhaps tautological truth, there are criteria of progress towards the truth, as I shall explain presently. The status of truth in the objective sense, as correspondence to the facts, and its role as a regulative principle, may be compared to that of a mountain peak, usually wrapped in clouds. A climber may not merely have difficulties in getting there, he may not know when he gets there, because he may be unable to distinguish, in the clouds, between the main summit and a subsidiary peak. Yet, this does not affect the objective existence of the summit, and if the climber tells us, "I doubt whether I reached the actual summit," then he does, by implication, recognize the objective existence of the summit. The very idea of error or of doubt, in its normal straightforward sense, implies the idea of an objective truth which we may fail to reach. Though it may be impossible for the climber ever to make sure that he has reached the summit, it will often be easy for him to realize that he has not reached it, or not yet reached it. For example, when he is turned back by an overhanging wall. Similarly, there will be cases when we are quite sure that we have not reached the truth. Thus, while coherence or consistency is no criterion of truth, simply because even demonstrably consistent systems may be false in fact, incoherence or inconsistency do establish falsity. So, if we are lucky, we may discover the falsity of some of our theories. In 1944, when Tarski published the first English outline of his investigations into the theory of truth, which he had published in Poland in 1933, few philosophers would have dared to make assertions like those of Xenophanes. And it is interesting that the volume in which Tarski's paper was published also contained two subjectivist papers on truth. Though things have improved since then, subjectivism is still rampant in the philosophy of science, and especially in the field of probability theory. The subjectivist theory of probability, which interprets degrees of probability as degrees of rational belief, stems directly from the subjectivist approach to truth, especially from the coherence theory. Yet it is still embraced by philosophers who have accepted Tarski's theory of truth. At least some of them, I suspect, have turned to probability theory in the hope that it would give them what they had originally expected from a subjectivist or epistemological theory of the attainment of truth through verification. That is, a theory of rational and justifiable belief based upon observed instances. It is an awkward point in all these subjectivist theories that they are irrefutable, in the sense that they can too easily evade any criticism. For it is always possible to uphold the view that everything we say about the world, or everything we print about logarithms, should be replaced by a belief statement. Thus we may replace the statement, "Snow is white," by "I believe that snow is white," or perhaps even by, "In the light of all the available evidence, I believe that it is rational to believe that snow is white." That we can, in a way, replace assertions about the objective world by one of these subjectivist circumlocutions is trivial, although in the case of the assertions found in logarithm tables, which might well be produced by machines, somewhat unconvincing. It may be mentioned in passing that the subjectivist interpretation of logical probability links these subjectivist replacements, exactly as in the case of the coherence theory of truth, with an approach which, on closer analysis, turns out to be essentially syntactic rather than semantic, though it may be presented within a semantical system. It may be useful to sum up the relationships between the objective and subjective theories of scientific knowledge with the help of a little table. Please view your screen now to see the table, and I will also be reading the table out loud. It contains 2 columns, and I will be reading it from left to right. On the left-hand side, we have objective or logical or ontological theories, as opposed to, and on the right-hand side, subjective or psychological or epistemological theories. Back on the left, we have truth as correspondence with the facts, as opposed to truth as property of our state of mind or knowledge or belief. Back on the left, we have objective probability, inherent in the situation and testable by statistical tests, as opposed to subjective probability, degree of rational belief based upon our total knowledge. Back on the left, we have objective randomness, statistically testable, as opposed to lack of knowledge. And on the left again, we have equiprobability, physical or situational symmetry, as opposed to lack of knowledge. In all these cases, I am inclined to say not only that these two approaches should be distinguished, but also that the subjectivist approach should be discarded as a lapse, as based on a mistake, though perhaps a tempting mistake. There is, however, a similar table in which the epistemological right-hand side is not based on a mistake. Please view the screen now to see the table. This table also consists of 2 columns. On the left, we have truth, as, on the right, conjecture. On the left, testability as empirical test. On the left, explanatory or predictive power and verisimilitude as degree of corroboration, that is, report of the results of tests. 3. Truth and content, verisimilitude versus probability. Like many other philosophers, I am at times inclined to classify philosophers as belonging to two main groups, those with whom I disagree and those who agree with me. I might call them the verificationists or the justificationist philosophers of knowledge or of belief, and the falsificationists or fallibilists or critical philosophers of conjectural knowledge. I may mention in passing a third group with whom I also disagree. They may be called the disappointed justificationists, the irrationalists, and the skeptics. The members of the first group, the verificationists or justificationists, hold, roughly speaking, that whatever cannot be supported by positive reasons is unworthy of being believed, or even of being taken into serious consideration. On the other hand, the members of the second group, the falsificationists or fallibilists, say, roughly speaking, that what cannot, at present, in principle, be overthrown by criticism is, at present, unworthy of being seriously considered, while what can, in principle, be so overthrown, and yet resists all our critical efforts to do so, may quite possibly be false, but is, at any rate, not unworthy of being seriously considered, and perhaps even of being believed, though only tentatively. Verificationists, I admit, are eager to uphold the most important tradition of rationalism, the fight of reason against superstition and arbitrary authority. For they demand that we should accept a belief only if it can be justified by positive evidence, that is to say, shown to be true, or at least, to be highly probable. In other words, they demand that we should accept a belief only if it can be verified or probabilistically confirmed. Falsificationists, the group of fallibilists to which I belong, believe, as most irrationalists also believe, that they have discovered logical arguments which show that the program of the first group cannot be carried out, that we can never give positive reasons which justify the belief that a theory is true. But, unlike irrationalists, we falsificationists believe that we have also discovered a way to realize the old ideal of distinguishing rational science from various forms of superstition, in spite of the breakdown of the original inductivist or justificationist program. We hold that this ideal can be realized, very simply, by recognizing that the rationality of science lies not in its habit of appealing to empirical evidence in support of its dogmas. Astrologers do so too, but solely in the critical approach, in an attitude which, of course, involves the critical use, among other arguments, of empirical evidence, especially in refutations. For us, therefore, science has nothing to do with the quest for certainty or probability or reliability. We are not interested in establishing scientific theories as secure or certain or probable. Conscious of our fallibility, we are only interested in criticizing them and testing them, hoping to find out where we are mistaken, of learning from our mistakes, and, if we are lucky, of proceeding to better theories. Considering their views about the positive or negative function of argument in science, the first group, the justificationists, may be also nicknamed the positivists, and the second, the group to which I belong, the critics or the negativists. These are, of course, mere nicknames, yet they may perhaps suggest some of the reasons why some people believe that only the positivists or verificationists are seriously interested in truth and in the search for truth, while we, the critics or negativists, are flippant about the search for truth and addicted to barren and destructive criticism and to the propounding of views which are clearly paradoxal. This mistaken picture of our views seems to result largely from the adoption of a justificationist program and of the mistaken subjectivist approach to truth, which I have described. For the fact is that we too see science as the search for truth, and that, at least since Tarski, we are no longer afraid to say so. Indeed, it is only with respect to this aim, the discovery of truth, that we can say that though we are fallible, we hope to learn from our mistakes. It is only the idea of truth which allows us to speak sensibly of mistakes and of rational criticism, and which makes rational discussion possible. That is to say, critical discussion in search of mistakes with the serious purpose of eliminating as many of these mistakes as we can in order to get nearer to the truth. Thus, the very idea of error and of fallibility involves the idea of an objective truth as the standard of which we may fall short. It is in this sense that the idea of truth is a regulative idea. Thus, we accept the idea that the task of science is the search for truth, that is, for true theories, even though, as Xenophanes pointed out, we may never get them, or know them as true if we get them. Yet we also stress that truth is not the only aim of science. We want more than mere truth. What we look for is interesting truth, truth which is hard to come by. And in the natural sciences, as distinct from mathematics, what we look for is truth which has a high degree of explanatory power, in a sense which implies that it is logically improbable truth. For it is clear, first of all, that we do not merely want truth. We want more truth and new truth. We are not content with twice 2 equals 4, even though it is true. We do not resort to reciting the multiplication table if we are faced with a difficult problem in topology or in physics. Mere truth is not enough. What we look for are answers to our problems. The point has been well put by the German humorist and poet Busch, of Max and Moritz fame, in a little nursery rhyme. I mean, a rhyme for the epistemological nursery. Twice 2 equals 4, 'tis true, but too empty and too trite. What I look for is a clue to some matters not so light. Only if it is an answer to a problem, a difficult, a fertile problem, a problem of some depth, does a truth, or a conjecture about the truth, become relevant to science. This is so in pure mathematics, and it is so in the natural sciences. And in the latter, we have something like a logical measure of the depth or significance of the problem in the increase of logical improbability or explanatory power of the proposed new answer, as compared with the best theory or conjecture previously proposed in the field. This logical measure is essentially the same thing which I have described above as the logical criterion of potential satisfactoriness and of progress. My description of this situation might tempt some people to say that truth does not, after all, play a very big role with us negativists, even as a regulative principle. There can be no doubt, they will say, that negativists, like myself, much prefer an attempt to solve an interesting problem by a bold conjecture, even if it soon turns out to be false, to any recital of a sequence of true but uninteresting assertions. Thus it does not seem, after all, as if we negativists had much use for the idea of truth. Our ideas of scientific progress and of attempted problem solving do not seem very closely related to it. This, I believe, would give quite a mistaken impression of the attitude of our group. Call us negativists or what you like, but you should realize that we are as much interested in the truth as anybody, for example, as the members of a court of justice. When the judge tells a witness that he should speak the truth, the whole truth, and nothing but the truth, then what he looks for is as much of the relevant truth as the witness may be able to offer. A witness who likes to wander off into irrelevancies is unsatisfactory as a witness, even though these irrelevancies may be truisms, and thus part of the whole truth. It is quite obvious that what the judge, or anybody else, wants when he asks for the whole truth is as much interesting and relevant true information as can be got. And many perfectly candid witnesses have failed to disclose some important information simply because they were unaware of its relevance to the case. Thus, when we stress, with Bush, that we are not interested in mere truth, but in interesting and relevant truth, then I contend we only emphasize a point which everybody accepts. And if we are interested in bold conjectures, even if these should soon turn out to be false, then this interest is due to our methodological instinct that tells us that only with the help of such bold conjectures can we hope to discover interesting and relevant truth. There is a point here which, I suggest, it is the particular task of the logician to analyze. Interest or relevance, in the sense here intended, can be objectively analyzed. It is relative to our problems, and it depends on the explanatory power and thus on the content or improbability of the information. The measures alluded to earlier and developed in the addenda to this volume are precisely such measures as take account of some relative content of the information, its content relative to a hypothesis or to a problem. I can therefore gladly admit that falsificationists like myself much prefer an attempt to solve an interesting problem by a bold conjecture, even and especially if it soon turns out to be false, to any recital of a sequence of irrelevant truisms. We prefer this because we believe that this is the way in which we can learn from our mistakes, and that in finding that our conjecture was false, we shall have learnt much about the truth, and shall have got nearer to the truth. I therefore hold that both ideas, the idea of truth in the sense of correspondence with the facts, and the idea of content, which may be measured by the same measure as testability, play about equally important roles in our considerations, and that both can shed much light on the idea of progress in science. Looking at the progress of scientific knowledge, many people have been moved to say that even though we do not know how near to or how far from the truth we are, we can, and often do, approach more and more closely to the truth. I myself have sometimes said such things in the past, but always with a tinge of bad conscience. Not that I believe in being over fussy about what we say, as long as we speak as clearly as we can, yet do not pretend that what we are saying is clearer than it is, and as long as we do not try to derive apparently exact consequences from dubious or vague premises, there is no harm whatever in occasional vagueness, or in voicing every now and then our feelings and general intuitive impressions about things. Yet, whenever I used to write or to say something about science as getting nearer to the truth, or as a kind of approach to truth, I felt that I really ought to be writing truth with a capital T, in order to make it quite clear that a vague and metaphysical notion was involved here, in contradistinction to Tarski's truth, which we can, with a clear conscience, write in the ordinary way with small letters. It was only quite recently that I set myself to consider whether the idea of truth involved here was really so dangerously vague and metaphysical after all. Almost at once I found that it was not, and that there was no particular difficulty in applying Tarski's fundamental idea to it. For there is no reason whatever why we should not say that one theory corresponds better to the facts than another. This simple initial step makes everything clear. There really is no barrier here between what at first sight appeared to be truth with a capital T and truth in a Tarskian sense. But can we really speak about better correspondence? Are there such things as degrees of truth? Is it not dangerously misleading to talk as if Tarskian truth were located somewhere in a kind of metrical or at least topological space, so that we can sensibly say of two theories, say an earlier theory T1 and a later theory T2, that T2 has superseded T1 or progressed beyond T1 by approaching more closely to the truth than T1? I do not think that this kind of talk is at all misleading. On the contrary, I believe that we simply cannot do without something like this idea of a better or worse approximation to truth. For there is no doubt whatever that we can say, and often want to say, of a theory T2, that it corresponds better to the facts, or that, as far as we know, it seems to correspond better to the facts than another theory T1. I shall give here a somewhat unsystematic list of 6 types of cases in which we should be inclined to say of a theory T1 that it is superseded by T2, in the sense that T2 seems, as far as we know, to correspond better to the facts than T1, in some sense or another. 1. T2 makes more precise assertions than T1, and these more precise assertions stand up to more precise tests. 2. T2 takes account of and explains more facts than T1, which will include, for example, the above case that, other things being equal, T2's assertions are more precise. 3. T2 describes or explains the facts in more detail than T1. 4. T2 has passed tests which T1 has failed to pass. 5. T2 has suggested new experimental tests, not considered before T2 was designed, and not suggested by T1, and perhaps not even applicable to T1, and T2 has passed these tests. 6. T2 has unified or connected various hitherto unrelated problems. If we reflect upon this list, then we can see that the contents of the theories T1 and T2 play an important role in it. It will be remembered that the logical content of a statement or a theory A is the class of all statements which follow logically from A, while I have defined the empirical content of A as the class of all basic statements which contradict A. For in our list of 6 cases, the empirical content of theory T2 exceeds that of theory T1. This suggests that we combine here the ideas of truth and of content into one, the idea of a degree of better or worse correspondence to truth, or of greater or less likeness or similarity to truth, or to use a term already mentioned above, in contradistinction to probability, the idea of degrees of verisimilitude. It should be noted that the idea that every statement or theory is not only either true or false, but has, independently of its truth value, some degree of verisimilitude, does not give rise to any multi-valued logic, that is, to a logical system with more than 2 truth values, true and false. Though some of the things the defenders of multi-valued logic are hankering after seem to be realized by the theory of verisimilitude and related theories alluded to in section 3 of the addenda to this volume. Once I had seen the problem, it did not take me long to get to this point, but strangely enough, it took me a long time to put 2 and 2 together and to proceed from here to something like a simple definition of verisimilitude in terms of truth and of content. We can use either logical or empirical content and thus obtain 2 closely related ideas of verisimilitude, which, however, merge into one if we consider here only empirical theories or empirical aspects of theories. Let us consider the content of a statement A, that is, the class of all the logical consequences of A. If A is true, then this class can consist only of true statements, because truth is always transmitted from a premise to all its conclusions. But if A is false, then its content will always consist of both true and false consequences. Example, it always rains on Sundays is false, but its consequence that it rained last Sunday happens to be true. Thus, whenever a statement is true or false, there may be more truth or less truth in what it says, according to whether its content consists of a greater or a lesser number of true statements. Let us call the class of the true logical consequences of A the truth content of A, a German term Wahrheitsgehalt, reminiscent of the phrase, there is truth in what you say, of which truth content may be said to be a translation, has been intuitively used for a long time. And let us call the class of the false consequences of A, but only these, the falsity content of A. The falsity content is not, strictly speaking, a content because it does not contain any of the true conclusions of the false statements which forms its elements. Yet it is possible, see the addenda, to define its measure with the help of 2 contents. These terms are precisely as objective as the terms true or false and content themselves. Now we can say, assuming that the truth content and the falsity content of 2 theories, T1 and T2, are comparable, we can say that T2 is more closely similar to the truth or corresponds better to the facts than T1 if and only if either A, the truth content but not the falsity content of T2 exceeds that of T1, or B, the falsity content of T1 but not its truth content exceeds that of T2. If we now work with the perhaps fictitious assumption that the content and truth content of a theory A are in principle measurable, then we can go slightly beyond this definition and we can define VSA, that is to say, a measure of the verisimilitude or truth-likeness of A. The simplest definition will be VSA equals CTTA minus CTFA, where CTTA is a measure of the truth content of A, and CTFA is a measure of the falsity content of A. A slightly more complicated but in some respects preferable definition will be found in section 3 of the addenda to the present volume. It is obvious that VSA satisfies our 2 demands, according to which VSA should increase A, if CTTA increases while CTFA does not, and B, if CTFA decreases while CTTA does not. Some further considerations of a slightly technical nature and the definitions of CTTA and especially CTFA and VSA will be found in the addenda. Here I want only to discuss 3 non-technical points. The first point is this. Our idea of approximation to truth, or of verisimilitude, has the same objective character and the same ideal or regulative character as the idea of objective or absolute truth. It is not an epistemological or an epistemic idea, no more than is truth or content. In Tarski's terminology, it is obviously a semantic idea, like truth, or like logical consequence, and therefore content. Accordingly, we have here again to distinguish between the question, what do you intend to say if you say that the theory T2 has a higher degree of verisimilitude than the theory T1? And the question, how do you know that the theory T2 has a higher degree of verisimilitude than the theory T1? We have so far answered only the first question. The answer to the second question depends on it, and it is exactly analogous to the answer to the analogous, absolute rather than comparative, question about truth. I do not know, I only guess, but I can examine my guess critically, and if it withstands severe criticism, then this fact may be taken as a good critical reason in favour of it. My second point is this. Verisimilitude is so defined that maximum verisimilitude would be achieved only by a theory which is not only true, but completely comprehensively true, if it corresponds to all facts, as it were, and of course, only to real facts. This is, of course, a much more remote and unattainable ideal than a mere correspondence with some facts, as in, say, snow is usually white. But all this holds only for the maximum degree of verisimilitude, and not for the comparison of theories with respect to their degree of verisimilitude. This comparative use of the idea is its main point, and the idea of a higher or lower degree of verisimilitude seems less remote and more applicable, and therefore perhaps more important for the analysis of scientific methods than the, in itself much more fundamental, idea of absolute truth itself. This leads me to my third point. Let me first say that I do not suggest that the explicit introduction of the idea of verisimilitude will lead to any changes in the theory of method. On the contrary, I think that my theory of testability or corroboration by empirical tests is the proper methodological counterpart to this new metalogical idea. The only improvement is one of clarification. Thus, I have often said that we prefer the theory T2, which has passed certain severe tests, to the theory T1, which has failed these tests, because a false theory is certainly worse than one which, for all we know, may be true. To this, we can now add that even after T2 has been refuted in its turn, we can still say that it is better than T1, for although both have been shown to be false, the fact that T2 has withstood tests which T1 did not pass may be a good indication that the falsity content of T1 exceeds that of T2, while its truth content does not. Thus, we may still give preference to T2, even after its falsification, because we have reason to think that it agrees better with the facts than did T1. All cases where we accept T2 because of experiments which were crucial between T2 and T1 seem to be of this kind, and especially all cases where the experiments were found by trying to think out, with the help of T2, cases where T2 leads to other results than did T1. Thus, Newton's theory allowed us to predict some deviations from Kepler's laws. Its success in this field established that it did not fail in cases which refuted Kepler's. At least, the now known falsity content of Kepler's theory was not part of Newton's, while it was pretty clear that the truth content could not have shrunk, since Kepler's theory followed from Newton's as a first approximation. Similarly, a theory T2, which is more precise than T1, can now be shown to have, always provided its falsity content does not exceed that of T1, a higher degree of verisimilitude than T1. The same will hold for T2, whose numerical assertions, though false, come nearer to the true numerical values than those of T1. Ultimately, the idea of verisimilitude is most important in cases where we know that we have to work with theories which are, at best, approximations. That is to say, theories of which we actually know that they cannot be true. This is often the case in the social sciences. In these cases, we can speak of better or worse approximations to the truth, and we therefore do not need to interpret these cases in an instrumentalist sense. It always remains possible, of course, that we shall make mistakes in our relative appraisal of two theories, and the appraisal will often be a controversial matter. This point can hardly be overemphasized. Yet it is also important that, in principle, and as long as there are no revolutionary changes in our background knowledge, the relative appraisal of our two theories, T1 and T2, will remain stable. More particularly, our preferences need not change, as we have seen, if we eventually refute the better of the two theories. Newton's dynamics, for example, even though we may regard it as refuted, has of course maintained its superiority over Kepler's and Galileo's theories. The reason is its greater content or explanatory power. Newton's theory continues to explain more facts than did the others, to explain them with greater precision, and to unify the previously unconnected problems of celestial and terrestrial mechanics. The reason for the stability of relative appraisals such as these is quite simple. The logical relation between the theories is of such a character that, first of all, there exist with respect to them those crucial experiments, and these, when carried out, went against Newton's predecessors. And secondly, it is of such a character that the later refutations of Newton's theory could not support the older theories. They either did not affect them, or, as with the perihelion motion of Mercury, they could be claimed to refute the predecessors also. I hope that I have explained the idea of better agreement with the facts, or of degrees of verisimilitude, sufficiently clearly for the purpose of this brief summary. A brief remark on the early history of the confusion between verisimilitude and probability may perhaps be appropriate here. As we have seen, progress in science means progress towards more interesting, less trivial, and therefore less probable theories, where probable is taken in any sense, such as lack of content or greater statistical frequency that satisfies the calculus of probability. And this means, as a rule, progress towards less familiar and less comfortable or plausible theories. Yet the idea of greater verisimilitude, of a better approximation to the truth, is usually confused, intuitively, with the totally different idea of a greater probability, in its various senses of more likely than not, more often than not, seems likely to be true, sounds plausible, sounds convincing. The confusion is a very old one. We have only to remember some of the other words for probable, such as likely, which comes originally from like the truth, or verisimilar, iokotos, and ikos, etc. in Greek, verisimilis in Latin, and wahrscheinlich in German, in order to see some of the traces, and perhaps some of the sources of this confusion. Two, at least, of the earliest of the pre-Socratic philosophers used iokota in the sense of like the truth, or similar to the truth. Thus we read in Xenophanes, these things, let us suppose, are like the truth. It is fairly clear that verisimilitude or truth-likeness is meant here, rather than probability or degree of incomplete certainty. Otherwise, the words "let us suppose" or "let it be conjectured" or "let it be imagined" would be redundant, and Xenophanes would have written something like, "These things, let it be said, are probable." Using the same word, iokota, Parmenides wrote, "Now of this world thus arranged to seem wholly like the truth, I shall tell you." Yet already in the same generation or the next, Hippochamus, in a criticism of Xenophanes, seems to have used the word iokotos in the sense of plausible or something like it, though the possibility cannot be excluded that he may have used it in the sense of like the truth, and that it was Aristotle who read it in the sense of plausible or likely. Some 3 generations later, however, iokos is used quite unambiguously in the sense of likely or probable, or perhaps even of more frequently than not, by the sophist Antiphon when he writes, "If one begins a thing well, it is likely to end well." All this suggests that the confusion between verisimilitude and probability goes back almost to the beginning of Western philosophy, and this is understandable if we consider that Xenophanes stressed the fallibility of our knowledge, which he described as uncertain guesswork, and at best, like the truth. This phrase, it seems, lent itself to misinterpretation as uncertain and, at best, of some fair degree of certainty, that is, probable. Xenophanes himself seems to have distinguished clearly between degrees of certainty and degrees of truth-likeness. This emerges from another fragment, quoted above towards the end of chapter 5, page 153, which says that even by chance we were to hit upon and pronounce the final truth, that is, we may add, perfect truth-likeness, we should not know it. Thus, great uncertainty is compatible with greatest truth-likeness. I suggest that we return to Xenophanes and reintroduce a clear distinction between verisimilitude and probability, using this latter term in a sense laid down by the calculus of probability. The differentiation between these 2 ideas is the more important as they have become confused, because both are closely related to the idea of truth, and both introduce the idea of an approach to truth by degrees. Logical probability, we do not discuss here physical probability, represents the idea of approaching logical certainty or tautological truth through a gradual diminution of informative content. Verisimilitude, on the other hand, represents the idea of approaching comprehensive truth. It thus combines truth and content, while probability combines truth with lack of content. The feeling that it is absurd of me to deny that science aims at probability stems, I suggest, from a misguided intuition, from the intuitive confusion between the 2 notions of verisimilitude and of probability, which, as it now turns out, are utterly different. 4. Background knowledge and scientific growth. People involved in a fruitful critical discussion of a problem often rely, if only unconsciously, upon 2 things: the acceptance by all parties of the common aim of getting at the truth, or at least nearer to the truth, and a considerable amount of common background knowledge. This does not mean that either of these 2 things is an indispensable basis of every discussion, or that these 2 things are themselves a priori and cannot be critically discussed in their turn. It only means that criticism never starts from nothing, even though every one of its starting points may be challenged, one at a time, in the course of the critical debate. Yet, though every one of our assumptions may be challenged, it is quite impracticable to challenge all of them at the same time. Thus, all criticism must be piecemeal, as against the holistic view of Dewham and of Quinn, which is only another way of saying that the fundamental maxim of every critical discussion is that we should stick to our problem and that we should subdivide it, if practicable, and try to solve no more than one problem at a time, although we may, of course, always proceed to a subsidiary problem or replace our problem by a better one. While discussing a problem, we always accept, if only temporarily, all kinds of things as unproblematic. They constitute, for the time being, and for the discussion of this particular problem, what I call our background knowledge. Few parts of this background knowledge will appear to us in all contexts as absolutely unproblematic, and any particular part of it may be challenged at any time, especially if we suspect that its uncritical acceptance may be responsible for some of our difficulties. But almost all of the vast amount of background knowledge which we constantly use in any informal discussion will, for practical reasons, necessarily remain unquestioned, and the misguided attempt to question it all, that is to say, to start from scratch, can easily lead to the breakdown of a critical debate. Were we to start the race where Adam started, I know of no reason why we should get any further than Adam did. The fact that, as a rule, we are at any given moment taking a vast amount of traditional knowledge for granted, for almost all our knowledge is traditional, creates no difficulty for the falsificationist or fallibilist, for he does not accept this background knowledge, neither as established, nor as fairly certain, nor yet as probable. He knows that even its tentative acceptance is risky, and stresses that every bit of it is open to criticism, even though only in a piecemeal way. We can never be certain that we shall challenge the right bit, but since our quest is not for certainty, this does not matter. It will be noticed that this remark contains my answer to Quinn's holistic view of empirical tests, a view which Quinn formulates, with reference to Dewham, by asserting that our statements about the external world face the tribunal of sense experience not individually, but only as a corporate body. Now, it has to be admitted that we can often test only a large chunk of a theoretical system, and sometimes perhaps only the whole system, and that, in these cases, it is sheer guesswork which of its ingredients should be held responsible for any falsification, a point which I have tried to emphasize, also with reference to Dewham, for a long time past. Though this argument may turn a verificationist into a skeptic, it does not affect those who hold that our theories are guesses anyway. This shows that the holistic view of tests, even if it were true, would not create a serious difficulty for the fallibilist and falsificationist. On the other hand, it should be said that the holistic argument goes much too far. It is possible in quite a few cases to find which hypothesis is responsible for the refutation, or in other words, which part or group of hypotheses was necessary for the derivation of the refuted prediction. The fact that such logical dependencies may be discovered is established by the practice of independence proofs of axiomatized systems. Proofs which show that certain axioms of an axiomatic system cannot be derived from the rest. The more simple of these proofs consist in the construction, or rather in the discovery, of a model, a set of things, relations, operations, or functions, which satisfies all the axioms except the one whose independence is to be shown. For this one axiom, and therefore for the theory as a whole, the model constitutes a counterexample. Now, let us say that we have an axiomatized theoretical system, for example, of physics, which allows us to predict that certain things do not happen, and that we discover a counterexample. There is no reason whatever why this counterexample may not be found to satisfy most of our axioms, or even all our axioms, except one whose independence would be thus established. This shows that the holistic dogma of the global character of all tests or counterexamples is untenable, and it explains why, even without axiomatizing our physical theory, we may well have an inkling of what has gone wrong with our system. This, incidentally, speaks in favour of operating, in physics, with highly analysed theoretical systems, that is, with systems which, even though they may fuse all the hypotheses into one, allow us to separate various groups of hypotheses, each of which may become an object of refutation by counterexamples. An excellent recent example is the rejection, in atomic theory, of the law of parity. Another is the rejection of the law of commutation for conjugate variables, prior to their interpretation as matrices, and to the statistical interpretation of these matrices. One fact which is characteristic of the situation in which the scientist finds himself is that we constantly add to our background knowledge. If we discard some parts of it, others, closely related to them, will remain. For example, even though we may regard Newton's theory as refuted, that is, his system of ideas, and the formal deductive system which derives from it, we may still assume, as part of our background knowledge, the approximate truth of its quantitative formulae. The existence of this background knowledge plays an important role in one of the arguments which support, I believe, my theses that the rational and empirical character of science would vanish if it ceased to progress. I can sketch this argument here only in its barest outline. A serious empirical test always consists in the attempt to find a refutation, a counterexample. In the search for a counterexample, we have to use our background knowledge, for we always try to refute first the most risky predictions, the most unlikely consequences, as Peirce already saw, which means that we always look in the most probable kinds of places for the most probable kinds of counterexamples. Most probable in the sense that we should expect to find them in the light of our background knowledge. Now, if a theory stands up to many such tests, then, owing to the incorporation of the results of our tests into our background knowledge, there may be, after a time, no places left where, in the light of our new background knowledge, counterexamples can, with a high probability, be expected to occur. But this means that the degree of severity of our test declines. This is also the reason why an often repeated test will no longer be considered as significant or as severe. There is something like a law of diminishing returns from repeated tests, as opposed to tests which, in the light of our background knowledge, are of a new kind, and which therefore may still be felt to be significant. These are the facts that are inherent in the knowledge situation, and they have often been described, especially by John Maynard Keynes and by Ernest Nagel, as difficult to explain by an inductivist theory of science. But for us, it is all very easy, and we can even explain, by a similar analysis of the knowledge situation, why the empirical character of a very successful theory always grows stale after a time. We may then feel, as Poincare did with respect to Newton's theory, that the theory is nothing but a set of implicit definitions or conventions, until we progress again and, by refuting it, incidentally re-establish its lost empirical character. De mortuis nil nisi bene. Once a theory is refuted, its empirical character is secure and shines without blemish. 5. 3 requirements for the growth of knowledge. But let us return again to the idea of getting nearer to the truth, to the search for theories that agree better with the facts, as indicated by the list of 6 comparisons in section 5 above. What is the general problem situation in which the scientist finds himself? He has before him a scientific problem. He wants to find a new theory capable of explaining certain empirical facts, facts which the earlier theories successfully explained, others which they could not explain, and some by which they were actually falsified. The new theory should also resolve, if possible, some theoretical difficulties, such as how to dispense with certain ad hoc hypotheses, or how to unify 2 theories. Now, if he manages to produce a theory which is a solution to all these problems, his achievement will be very great. Yet, it is not enough. I have been asked, what more do you want? My answer is that there are many more things which I want, or rather, which I think are required by the logic of the general problem situation in which the scientist finds himself, by the task of getting nearer to the truth. I shall confine myself here to the discussion of 3 such requirements. The first requirement is this: the new theory should proceed from some simple, new, and powerful unifying idea about some connection or relation, such as gravitational attraction, between hitherto unconnected things, such as planets and apples, or facts, such as inertial and gravitational mass, or new theoretical entities, such as fields and particles. This requirement of simplicity is a bit vague, and it seems difficult to formulate it very clearly. It seems to be intimately connected with the idea that our theories should describe the structural properties of the world, an idea which is hard to think out fully without getting involved in an infinite regress. This is so because any idea of a particular structure of the world, unless indeed we think of a purely mathematical structure, already presupposes a universal theory. For example, explaining the laws of chemistry by interpreting molecules as structures of atoms or of subatomic particles presupposes the idea of universal laws that regulate the properties and the behavior of the atoms and of the particles. Yet one important ingredient in the idea of simplicity can be logically analyzed. It is the idea of testability. This leads us immediately to our second requirement. For secondly, we require that the new theory should be independently testable. That is to say, apart from explaining all the explander, which the new theory was designed to explain, it must have new and testable consequences, preferably consequences of a new kind. It must lead to the prediction of phenomena which have not so far been observed. This requirement seems to me indispensable, since without it, our new theory might be ad hoc, for it is always possible to produce a theory to fit any given set of explicanda. Thus, our 2 first requirements are needed in order to restrict the range of our choice among the possible solutions, many of them uninteresting, of the problem in hand. If our second requirement is satisfied, then our new theory will represent a potential step forward, whatever the outcome of the new tests may be. For it will be better testable than the previous theory. The fact that it explains all the explicanda of the previous theory, and that, in addition, it gives rise to new tests, suffices to ensure this. Moreover, the second requirement also ensures that our new theory will, to some extent, be fruitful as an instrument of exploration. That is to say, it will suggest to us new experiments, and even if these should, at once, lead to the refutation of the theory, our factual knowledge will have grown through the unexpected results of the new experiments. Moreover, they will confront us with new problems to be solved by new explanatory theories. Yet, I believe that there must be a third requirement for a good theory. It is this: we require that the theory should pass some new and severe tests. Clearly, this requirement is totally different in character from the previous two. These could be seen to be fulfilled, or not fulfilled, largely by analysing the old and the new theories logically. They are formal requirements. The third requirement, on the other hand, can be found to be fulfilled, or not fulfilled, only by testing the new theory empirically. It is a material requirement, a requirement of empirical success. Moreover, the third requirement clearly cannot be indispensable in the same sense as are the two previous ones. For these two are indispensable for deciding whether the theory in question should be at all accepted as a serious candidate for examination by empirical tests, or in other words, whether it is an interesting and promising theory. Yet, on the other hand, some of the most interesting and most admirable theories ever conceived were refuted at the very first test. And why not? The most promising theory may fail if it makes predictions of a new kind. An example is the marvelous theory of Bohr, Kramers, and Slater of 1924, which, as an intellectual achievement, might perhaps even rank with Bohr's theory of the hydrogen atom of 1913. Yet, unfortunately, it was almost at once refuted by the facts, by the coincidence experiments of Bose and Geiger. This shows that not even the greatest physicist can anticipate the secrets of nature. His inspirations can only be guesses, and it is no fault of his, or of his theory, if it is refuted. Even Newton's theory was in the end refuted, and indeed, we hope that we shall in this way succeed in refuting and improving upon every new theory. And if it is refuted in the end, why not in the beginning? One might well say that it is merely a historical accident if a theory is refuted after 6 months rather than after 6 years or 600 years. Refutations have often been regarded as establishing the failure of the scientist, or at least of his theory. It should be stressed that this is an inductivist error. Every refutation should be regarded as a great success, not merely as a success of the scientist who refuted the theory, but also of the scientist who created the refuted theory and who thus, in the first instance, suggested, if only indirectly, the refuting experiment. Even if a new theory, such as the theory of Bohr, Kramers, and Slater, should meet an early death, it should not be forgotten. Rather, its beauty should be remembered, and history should record our gratitude to it for bequeathing to us new and perhaps still unexplained experimental facts and, with them, new problems, and for the services it has thus rendered to the progress of science during its successful but short life. All this indicates clearly that our third requirement is not indispensable. Even a theory that fails to meet it can make an important contribution to science. Yet, in a different sense, I hold, it is indispensable nonetheless. Bohr, Kramers, and Slater rightly aimed at more than making an important contribution to science. In the first place, I contend that further progress in science would become impossible if we did not reasonably often manage to meet the third requirement. Thus, if the progress of science is to continue, and its rationality not to decline, we need not only successful refutations, but also positive successes. We must, that is, manage reasonably often to produce theories that entail new predictions, especially predictions of new effects, new testable consequences, suggested by the new theory and never thought of before. Such a new prediction was that planets would, under certain circumstances, deviate from Kepler's laws, or that light, in spite of its zero mass, would prove to be subject to gravitational attraction, that is, Einstein's eclipse effect. Another example is Dirac's prediction that there will be an antiparticle for every elementary particle. New predictions of these kinds must not only be produced, but they must also be reasonably often corroborated by experimental evidence, I contend, if scientific progress is to continue. We do need this kind of success. It is not for nothing that the great theories of science have all meant a new conquest of the unknown, a new success in predicting what had never been thought of before. We need successes such as that of Dirac, whose antiparticles have survived the abandonment of some other parts of his theories, or that of Yakowa's meson theory. We need the success, the empirical corroboration of some of our theories, if only in order to appreciate the significance of successful and stirring refutations, like that of parody. It seems to me quite clear that it is only through these temporary successes of our theories that we can be reasonably successful in attributing our refutations to definite portions of the theoretical maze. For we are reasonably successful in this, a fact which must remain inexplicable for one who adopts Duham's and Quinn's view on the matter. An unbroken sequence of refuted theories would soon leave us bewildered and helpless. We should have no clue about the parts of each of these theories, or of our background knowledge, to which we might, tentatively, attribute the failure of that theory. Earlier, I suggested that science would stagnate and lose its empirical character if we should fail to obtain refutations. We can now see that, for very similar reasons, science would stagnate and lose its empirical character if we should fail to obtain verifications of new predictions. That is, if we should only manage to produce theories that satisfy our first two requirements, but not the third. For suppose we were to produce an unbroken sequence of explanatory theories, each of which would explain all the explicanda in its field, including the experiments which refuted its predecessors. Each would also be independently testable by predicted new effects, yet each would be at once refuted when these predictions were put to the test. Thus, each would satisfy our first two requirements, but all would fail to satisfy the third. I assert that, in this case, we should feel that we were producing a sequence of theories which, in spite of their increasing degree of testability, were ad hoc, and that we were not getting any nearer to the truth. And indeed, this feeling may well be justified. This whole sequence of theories might easily be ad hoc. For if it is admitted that a theory may be ad hoc if it is not independently testable by experiments of a new kind, but merely explains all the explicanda, including the experiments which refuted its predecessors, then it is clear that the mere fact that the theory is also independently testable cannot as such ensure that it is not ad hoc. This becomes clear if we consider that it is always possible, by a trivial stratagem, to make an ad hoc theory independently testable, if we do not also require that it should pass the independent tests in question. We merely have to connect it, conjunctively, in some way or other, with any testable but not yet tested fantastic ad hoc prediction which may occur to us, or to some science fiction writer. Thus, our third requirement, like the second, is needed in order to eliminate trivial and other ad hoc theories, but it is needed also for what seem to me even more serious reasons. I think that we are quite right to expect, and perhaps even to hope, that even our best theories will be superseded and replaced by better ones, though we may at the same time feel the need for encouragement in our belief that we are making progress. Yet this should certainly not induce in us the attitude of merely producing theories so that they can be superseded. For our aim as scientists is to discover the truth about our problem, and we must look at our theories as serious attempts to find the truth. If they are not true, they may be, admittedly, important stepping stones towards the truth, instruments for further discoveries. But this does not mean that we can ever be content to look at them as being nothing but stepping stones, nothing but instruments. For this would involve giving up even the view that they are instruments of theoretical discoveries. It would commit us to looking upon them as mere instruments for some observational or pragmatic purpose. And this approach would not, I suspect, be very successful, even from a pragmatic point of view. If we are content to look at our theories as mere stepping stones, then most of them will not even be good stepping stones. Thus, we ought not to aim at theories which are mere instruments for the exploration of facts, but we ought to try to find genuine explanatory theories. We should make genuine guesses about the structure of the world. In brief, we should not be satisfied with the first two requirements. Of course, the fulfillment of our third requirement is not in our own hands. No amount of ingenuity can ensure the construction of a successful theory. We also need luck, and we also need a world whose mathematical structure is not so intricate as to make progress impossible. For indeed, if we should cease to progress in the sense of our third requirement, if we should only succeed in refuting our theories, but not in obtaining some verifications of predictions of a new kind, we might well decide that our scientific problems have become too difficult for us, because the structure, if any, of the world is beyond our powers of comprehension. Even in this case, we might proceed, for a time, with theory construction, criticism, and falsification. The rational side of the method of science might, for a time, continue to function. Yet I believe that we should feel that, especially for the functioning of its empirical side, both kinds of successes are essential. Success in refuting our theories, and success on the part of some of our theories in resisting at least some of our most determined attempts to refute them. It may be objected that this is merely good psychological advice about the attitude which scientists ought to adopt, a matter which, after all, is their private affair, and that a theory of scientific method worthy of its name should be able to produce logical or methodological arguments in support of our third requirement. Instead of appealing to the attitude or the psychology of the scientist, our theory of science should even be able to explain his attitude and his psychology by an analysis of the logic of the situation in which he finds himself. There is a problem here for our theory of method. I accept this challenge, and I shall produce 3 objective reasons. The first from the idea of truth, the second from the idea of getting nearer to the truth, verisimilitude, and the third from our old idea of independent tests and of crucial tests. 1. The first reason why our requirement is so important is this. We know that if we had an independently testable theory which was, moreover, true, then it would provide us with successful predictions, and only with successful ones. Successful predictions, though they are not, of course, sufficient conditions for the truth of a theory, are therefore at least necessary conditions for the truth of an independently testable theory. In this sense, and only in this sense, our third requirement may even be said to be necessary, if we seriously accept truth as a regulative idea. 2. The second reason is this. If it is our aim to strengthen the verisimilitude of our theories, or to get nearer to the truth, then we should be anxious not only to reduce the falsity content of our theories, but also to strengthen their truth content. Admittedly, this may be done in certain cases simply by constructing the new theory in such a way that the refutations of the old theory are explained, saving the phenomena, in this case the refutations. But there are other cases of scientific progress, cases whose existence shows that this way of increasing the truth content is not the only possible one. The cases I have in mind are cases in which there was no refutation. Neither Galileo's nor Kepler's theory was refuted before Newton. What Newton tried to do was to explain them from more general assumptions, and thus to unify 2 hitherto unrelated fields of inquiry. The same may be said of many other theories. Ptolemy's system was not refuted when Copernicus produced his. And though there was, before Einstein, the puzzling experiment of Michelson and Morley, this had been successfully explained by Lorentz and Fitzgerald. It is in cases like these that crucial experiments become decisively important. We have no reason to regard the new theory as better than the old theory, to believe that it is nearer to the truth, until we have derived from the new theory new predictions which were unobtainable from the old theory, the phases of Venus, the perturbations, the mass-energy equation, and until we have found that these new predictions were successful. For it is only this success which shows that the new theory had true consequences, that is, a truth content, where the old theories had false consequences, that is, a falsity content. Had the new theory been refuted in any of these crucial experiments, then we should have had no reason to abandon the old one in its favour, even if the old theory was not wholly satisfactory. This was the fate of the Bohr-Kramers-Slater theory. In all these important cases, we need the new theory in order to find out where the old theory was deficient. Admittedly, the situation is different if the deficiency of the old theory is already known before the new theory is invented. But logically, the case has enough similarity with the other cases to regard a new theory which leads to new crucial experiments, Einstein's mass-energy equation, as superior to one which can save only the known phenomena, Lorentz-Fitzgerald. 3. The same point, the importance of crucial tests, can be made without appealing to the aim of increasing the verisimilitude of a theory by using an old argument of mine, the need to make the tests of our explanations independent. This need is a result of the growth of knowledge, of the incorporation of what was new and problematic knowledge into background knowledge, with a consequent loss of explanatory power to our theories. These are my main arguments. Our third requirement may be divided into two parts. First, we require of a good theory that it should be successful in some of its new predictions. Secondly, we require that it is not refuted too soon, that is, before it has been strikingly successful. Both requirements sound strange. The first because the logical relationship between a theory and any corroborating evidence cannot, it seems, be affected by the question whether the theory is temporally prior to the evidence. The second because if the theory is doomed to be refuted, its intrinsic value can hardly depend upon delaying the refutation. Our explanation of this slightly puzzling difficulty is simple enough. The successful new predictions which we require the new theory to produce are identical with the crucial tests which it must pass in order to become sufficiently interesting to be accepted as an advance upon its predecessor, and to be considered worthy of further experimental examination, which may eventually lead to its refutation. Yet the difficulty can hardly be resolved by an inductivist methodology. It is therefore not surprising that inductivists such as John Maynard Keynes have asserted that the value of predictions, in the sense of facts derived from the theory but previously not known, was imaginary. And indeed, if the value of a theory would lie merely in its relation to its evidential basis, then it would be logically irrelevant whether the supporting evidence precedes or follows in time the invention of the theory. Similarly, the great founders of the hypothetical method used to stress the saving of the phenomena, that is to say, the demand that the theory should explain known experience. Successful new prediction of new effects seems to be a late idea, for obvious reasons. I do not know when and with whom it originated, yet the distinction between the prediction of known effects and the prediction of new effects was hardly ever made explicitly. But it seems to me quite indispensable as a part of an epistemology which views science as progressing to better and better explanatory theories, that is, not merely to instruments of exploration, but to genuine explanations. Keen's objection that it is an historical accident whether this support was known before the theory was proposed or only afterwards so that it could attain the status of a prediction, overlooks the all-important fact that it is through our theories that we learn to observe. That is to say, to ask questions, which lead to new observations and to new interpretations. This is the way our observational knowledge grows. And the questions asked are, as a rule, crucial questions which may lead to answers that decide between competing theories. It is my thesis that it is the growth of our knowledge, our way of choosing between theories in a certain problem situation, which makes science rational. Now, both the idea of the growth of knowledge and that of a problem situation are, at least, historical ideas. This explains why another partially historical idea, that of a genuine prediction of evidence, it may be about past facts, not known when the theory was first proposed, may play an important role here, and why the apparently irrelevant time element may become relevant. I shall now briefly sum up our results with respect to the epistemologies of the two groups of philosophers I have dealt with, the Verificationists and the Falsificationists. While the Verificationists or Inductivists in vain try to show that scientific beliefs can be justified, or at least established as probable, and so encourage by their failure the retreat into irrationalism, we of the other group have found that we do not even want a highly probable theory. Equating rationality with the critical attitude, we look for theories which, however fallible, progress beyond their predecessors, which means that they can be more severely tested and stand up to some of the new tests. And while the verificationists laboured in vain to discover valid positive arguments in support of their beliefs, we for our part are satisfied that the rationality of a theory lies in the fact that we choose it because it is better than its predecessors, because it can be put to more severe tests, because it may even have passed them, if we are fortunate, and because it may, therefore, approach nearer to the truth.